Good morning, everyone. So I am the geography guy. Can we get the slides on the main screen? We don't usually get the big gigs, us geographers. I have a teenage son, and he does a lot of research on the internet, and he tells me that being a geographer is 10th on the list of world's least stressful jobs. I'm not sure I'd agree with him right now, but on any given day, maybe. I'm not only a geography guy, I'm also a technology guy, and I'm here today to talk to you about this fusion of geography and technology that we at Esri call the science of where. So I'm guessing that the last time many of you thought about geography, if you've ever thought about it, was in front of a blackboard, or maybe in front of an electronic whiteboard if you're of a younger generation, something like this. And at this point in our lives, geography is often presented to us as a sort of an earthly knowledge base that has to be learned off by rote. And quite frankly, that can put a lot of people off. But I'm hoping today to introduce you to a different form of geography, a form of geography that's a lot less dusty and a lot more digital. And my proposition for you today is that geography is actually a science with its own concepts, laws, and methodologies. A science that can help us understand how the physical manifestation of business, society, and environment actually comes about. And it's this promise of a deeper understanding that led my company, Esri, to produce the world's first geographic information system. And it's this promise of a deeper understanding that still keeps us and our customers passionate about the power of geography today. So what I hope to do over the next short while is introduce you to some of the basic concepts behind digital geography and the science of where. Look at a few use cases that I myself am involved in at the moment as illustrations, and then talk a little bit about emergent technologies, some of which you've already heard about this morning, and how they might affect the practice of digital geography and the application of the science of where. So this is Tobler's first law of geography. And I'll let you in on a little secret right now. There is no second law, right? He either ran out of steam or, I don't know. But basically, this says that we are more interested in things that happen closer to us. And it's a law beloved of Irish politicians, and it gave rise to the term parish pump politics, which we live with on a day-to-day basis. But when you think about it, it's not just politics that are local. Your propensity to travel to avail of goods, services, and even experiences in the case of holidays is ultimately governed by this law. And an understanding of how this law works can be used by providers to optimize where to place those goods and services and how to provide them. But it can also help businesses optimize their supply chains and their distribution networks to be more efficient and, importantly, more sustainable. Another fundamental concept behind the science of where is what we call map algebra. And it relates to the geographer's ability to plot almost any phenomena in space in a sort of a map layer, and then to overlay those map layers in what we call, well, what I call anyway, a map sandwich. And this allows us to explore spatial relationships between those layers, to determine trends, to identify hotspots and not spots in what are essentially a body of unrelated phenomena. And this is a powerful concept and ability of geography. And for me, this sets geography apart from many other forms of science, because we've no key pair relationships going on between this data. We're simply using the spatial index of the map to explore relationships in multivariate space. And finally, who knew it? Geographers have a form of mathematics all of their own called spatial topology. And this allows us to express how things are actually related to each other in space, whether they're overlapping or whether they're disjoint, whether they're connected to each other or contained by each other, and a whole host of other relationships. So, geographers, this gives us a fundamental digital language code that we can use to understand our world. And we can take these concepts of topology, map algebra, and distance decay and encode them in geographic information systems. And geographic information systems are uniquely well placed to answer a very specific set of questions that are inherently geographical. Questions like the ones on the screen here. The first and most basic is, where's my stuff, right? Where your stuff is whatever it is that you're interested in. Could be your customers, your assets, your staff, resources that you manage. Knowing that, you usually want to know what's the closest one to a given location, because according to Tobler's first law, that's the one that it's most optimum to interact with. Quite often, especially in utility scenarios, you want to know what parts of my stuff are my customers connected to. If you switch off a water pipe or a water valve, you want to know what customers is that going to affect, and ditto with broadband and electricity and gas and so on. Businesses, especially in the retail sector, are often very interested in the characteristics of the localities in which they're doing business. If you take a successful retail store, for instance, that's working in a catchment area, and there's something about that catchment area that's making it successful. And retailers often want to know, well, where can I find another one of those catchment areas that has those same characteristics? And that's a bit like oil companies exploring for oil. You want to know the geology of oil-bearing sands so that you can find more of them. And finally, there's the classic problem that we refer to as the traveling salesman problem, which is how do I visit a set of locations in an optimum fashion? I haven't mentioned them yet, but of course, maps figure large in the geographer's toolbox. And I always think if a picture paints 1,000 words, then surely a map must paint 1,000,000. And for me, one of the most useful aspects of a map is that it helps us gain that deeper understanding, because it helps us abstract signal from the noise. It helps us derive meaning from what can often be a complex and messy landscape in which we live. This on the slide is the area of Mumbai that featured at the start of the film Slumdog Millionaire. Anyone who remembers that film will remember that that was a very chaotic landscape. The image reveals the true complexity of that, but a map of the same area allows us to abstract some meaning from that complexity and allows our human brains to understand a lot more about what we need to know about that landscape. So maps give us this fantastic way to abstract complexity out of our landscapes. And globes do the same, but on a larger scale. Google Earth was the first generally available globe system. And it was truly revolutionary. We all downloaded it, and we zoomed in and had a look into our neighbor's back garden to figure out what the hell was going on there. And then we pulled back to get this sort of Commander Hatfield view of the Earth, or the blue planet. And this definitely holds an allure. And the allure for me is that it holds the promise that if we can visualize the Earth on a system like this, then maybe, just maybe, we can map it, measure it, analyze it, model it, and predict it on a system like this. Maps have always been used as a system of record. Everything from property registrations to planning applications to land administration are commonly recorded on maps. And latterly, these have, of course, been digital maps. This particular example is from Department of Agriculture in Northern Ireland, and it's the system they use to administer EU grants and subsidies. Those of you who know anything about these schemes will know that you're not allowed to claim on your neighbour's land or the hedge in between or environmental areas or heritage areas. Now, it might look here as if we're just sort of sketching on the map. But in fact, this is a topologically aware system where every mouse click fires a load of those topology rules that I mentioned earlier on to ensure compliance with the scheme regulations. And the feedback from this client was that this, in its first year of operation, helped them avoid a disallowance from the EU of £60 million, which is a pretty good return on investment. Maps provide a means of visualizing statistical information, and they're a great alternative to just using tables or graphs. This particular map comes from a project I'm working on with the Ordnance Survey, the Central Statistics Office, and the United Nations. And it's a project that seeks to map Ireland's progress against the UN Sustainable Development Goals. This particular map is of unemployment on the night of the 2016 census. And what I like about this map is that it's using colour to indicate the level of unemployment, the rate of unemployment, but it's using the size of the symbol to indicate the volume of unemployment. And immediately, a pattern of sort of northwest and southeast differences jump off the map at us. And it's exactly this sort of pattern that public policymakers are looking for when they plan the provision of social services. Retailers are avid users of location analytics. Where you put your store relative to the competition and to your customer base has obvious implications for its success. This map shows the location of Tesco stores, and we've added in competitor stores from Lidl and Aldi. And then we can, using our distance decay, Tobler's law, calculate a sort of a 20-minute drive time polygon around each of the Tesco stores. Should come on in a second. And again, using map algebra, we can take those polygons and intersect them with the competitor stores and just simply count how many competitors you have within a given distance of each of your stores and come up with a simple count that we can then turn into a sort of a competition index in a very simple way. Taking that a little bit further, what if you wanted to know what the market characteristics of each of those locations actually was? Here we're using a 5-minute drive time buffer around a site in West Dublin. And that's enabling us to drill down into many layers of statistical and demographic information that we have on a global basis and bring back infographics and tables in relation to the market potential of that site in several different categories. I'm really excited about what's been happening in the whole data visualization and data analysis space and the current trend towards fusing geography into those systems. This is an example of a BI-style system showing road safety authority on traffic accidents in Dublin. But this BI system is geographically aware, and here the map is fully integrated with the other elements on this dashboard. So suppose we wanted to see the potential outcome of a change to the speed limit in a particular area, as is actually proposed. We can click on the bubble diagram to select accidents that took place within the 30-kilometre zone and then see their distribution in both map and chart form. This is a really powerful contributor to true evidence-based decision-making. Everything doesn't have to be that complex. This is a system which simply assigns jobs to workers at locations and pushes that location with a map to their mobile phones. It allows dispatchers use location to optimize how they assign jobs and allows workers see context in the assignments they receive and to actually navigate to the jobs as well. The widespread use of mobile phones and location-aware apps is creating new opportunities for geography. This is a sweet example I came across recently from the city of Sandy Springs in Georgia. They get a feed from a system called Waze, which is used for navigation, directly into their GIS system. And when on the Waze feed a crash is detected, the coordinates of that crash are fed in through the GIS, and it works out all the CCTV cameras within a 500 feet buffer of that crash and archives the imagery for subsequent analysis, all without human intervention. It's quite a sweet little use of GIS. Much of what I've shown you are current use cases for digital geography. But like every other technology, digital geography is taking advantage of emergent technical developments. I want to call out a few of these. 3D visualization, the Internet of Things and sensor networks, and also finally artificial intelligence and machine learning. In geographic information, as in all other forms of digital, data volume is growing exponentially. This is LiDAR data for the centre of Dublin. For those of you who don't know, LiDAR is a bit like radar. It's an active sensor, usually flown on the underneath of an aircraft, and sends out pulses that record in X, Y space and Z space for elevation. And it creates these amazingly accurate point clouds. And the problem is these point clouds are huge. This particular one is 1.4 billion points. Yet, using modern GI technology, we can render, explore, and take very accurate measures from this just using a browser. And we can use those measures to create true 3D objects in 3D space to create, for instance, complete digital cities, as in this case here. And because these are real objects, we can carry out analysis on them. In this case, there's a proposed building in orange there, and we can work out the shadow that will cast on the park in the foreground at various different times of the day, and compare the proposal with the existing situation. In the future, I predict that all city planning and zoning, lease assignment, and property management will happen in 3D web scenes, just like this one. Sensor networks based on mobile phones and IoT devices are driving a massive increase in the amount, availability, and timeliness of geographic information. It's hard to overstate the impact of this and the potential it holds for a deeper understanding of how our planet works. Geographers are rising to the challenge by developing new methodologies and technologies for dealing with big data at the scale presented by these sorts of systems. The fundamental change that's going on here is that citizens are becoming the sensor. We're all carrying around with us mobile phones that are passively sensing our environment all of the time, and we're pushing information in through apps on those mobile phones. We have IoT sensors in our homes and in our cars and in our offices that are creating masses of data about particular forms of phenomenon. It can be pretty much anything. In this case, it's something to do with Airbnb. In this case, this heat map has been created from Instagram in Melbourne, Instagram images in Melbourne that are hashtagged with the word street art. And this allows us to take these time-space cubes, usually with some form of a nominal measurement of something, in this case street art, and create heat maps by plotting that information, looking at the density. This example is from the Ornella lifeboats, actually, and it looks at call-outs around our coasts. And the sort of hexagonal hexabins that you can see on this, or hopefully just about make out, they illustrate a new method that geographers have come up with for visualizing large collections of big data at scale. So if you try and draw a couple of million points on a map, you're going to fail because you just get whiteout. Hexabins are a way of dynamically aggregating that information on the fly in real time so that you can make some sense out of it visually, and the computer can also carry out analysis on it. The problem that we are experiencing and addressing with big data is that I referred to earlier about trying to detect the signal in the noise when both the signal and the noise data are so immense. And this is where machine learning may have a role to play. The example on the top right is a 3D frequency map computed from over 400 million taxi trips in New York, pickups and drop-offs and time of day, 800 million points. And it shows us something, it tells us something about the taxi market in New York, and it could be used, for instance, by Uber to generate surge pricing for their service. But it also tells us something else. It tells us where humans are in New York at any given time of the day. And I've heard this information referred to recently as human weather. And just like ordinary weather, it's actually possible to forecast this. And the example in the bottom is from Kuwait City, where my colleague Mansour Rad has been working on their traffic records and using artificial intelligence and deep learning to actually forecast what the traffic will be like on a particular date and time of day. Slightly boring slide, but stick with me. Power companies, in this case Georgia Power, have to inspect their assets on a routine basis. This involves flying thousands of miles of power line and taking video and stills of asset condition. Now, a single mile of flight creates about 400 images to be inspected, and Georgia Power have 17,000 miles of power line. So my friends in Esri have worked with Georgia Power and IBM and their Watson Analytics system to create a solution that integrates geography and deep learning. In this clip, the feed from the helicopter is being fed into the GIS and on into Watson. And Watson is trained to pick up damaged transformers and plot them in red on the map for future attention, again, without any human intervention. So where's it all going? Well, the science of where is advancing, as evidenced by some of the examples I've shown you. We're developing the tools to map, model, measure, analyze and predict how our physical, built and socioeconomic environment works at scale. And the question I've become aware of lately is, can we now build a digital twin of the Earth? Well, I'm not sure we're in a position to do that quite yet, but one of the more interesting discussions I've been involved in lately was with the Port of Rotterdam, it's a customer of ours, and again, IBM, by coincidence. And Rotterdam is the busiest port in the world, with one ship movement every 6 minutes. It's shallow over there in Holland, and they have very tight tolerances. If a ship goes aground, there's huge disruption and massive fines. So they embarked on a project to attempt to build a digital twin of the port. Now, digital twins are usually discussed in the context of objects like jet engines and race cars, etc. This is the first time I've seen someone try to build a digital twin at geographic scale. And they started with mapping the exact location and characteristic of every single asset in a 40 square kilometre area. And they are now starting to build sensor networks that will inform them of how objects are moving around in that space. And it's the first attempt at a sort of a geographical digital twin. It's the first attempt to build something that goes back to that promise that was held, perhaps by Google Earth, that if you could visualize something in a Google Earth way, maybe, just maybe, you could manage it in that way as well. So the vision here is that Rotterdam already handles the biggest ships in the world, but in the future, those ships are going to be autonomous ships. We've heard about driverless cars. Just think about an autonomous ship and the size of that thing. And the vision is that intelligent docks, like the one in red on the map here, are going to be able to call out to a ship as it comes into the port and say, here I am, you can come and berth beside me, and the depth under your keel is going to be 11 centimeters, I think, is the tolerance they're working to. So 40 square kilometers is a small area, but it's a good start. And we always have had this view in Esri that the work that our customers do builds up and accretes over time into a sort of a little postage stamps on the surface of the Earth that give us a deeper understanding and build up a global digital atlas of the world with all the work that's going on. And perhaps in the future, I'll leave you with this thought, we will actually be able to apply process models to all of that information to such an extent that we will actually have a digital twin of the Earth. Thank you very much.